I'm just going to quickly sketch an answer to practice question 4 from week 2. So this question was asking about the results of an aptitude test that a friend of mine recently had to do when applying for a graduate position. And the first question, A, says, why did the results say that the individual's test score on its own does not provide a meaningful indication? And the answer to this one in brief is that what you got for a test, the absolute value is less important than a relative value. So it's how you compare to other people who sat this test that's important, as opposed to the test score itself. Part B asks us about this particular graph, which we're told in the blurb is a normal distribution, which reflects results of all graduates who sit this test. And it says, which of these probability functions is this graph? Is it a probability mass function? Well, that is the name given that's used for a discrete probability distribution. And a discrete probability distribution doesn't have this smooth shape. A discrete probability distribution, if it was to follow this general pattern, would have it more like something like this. So a probability mass function for a discrete variable can only take particular values, and it has this these bars rather than a continuous function. So then, is it a probability density function or a cumulative distribution function? This, in fact, is a probability density function, which shows us that the observations are most dense in this middle region here. The density is being measured here, probability density. So the density is highest, the most observations or most probable values are in here. The density is very low when we get down to either tail of the distribution. It is a probability density function as opposed to a cumulative distribution function because it is rising up to the most dense and then falls down to 0. For a cumulative distribution function, it would start similar. It's showing the cumulative distribution function, remember, is showing the probability of getting less than a particular x value. So it's the area, and as the x values get higher, the area gets higher. So this cumulative distribution function will always get larger. It's monotonically increasing, as you might have heard in one of Greg's classes. So it's rising at a faster rate. Then after the mean, that middle value, it starts to slow down, and eventually it has, in this case, an asymptote of 1. So this is the cumulative distribution function for a continuous distribution. This is the PDF that we have been shown. Then it says, what is the name given to the statistic of 68% referred to above? So in the question, this 68% is that your score on the test exceeded 68% of a sample of graduates, and that's your score there being measured along this axis, or perhaps a standardized version of it. The 68% figure is your percentile rank. It's saying that you scored greater than or the same as 68% of all other graduates. And it says, are you able to mark this figure on the accompanying graph? Yeah, well, that 68% is actually this area under the curve to the left of your test score. So no, it's not a measurement on this scale here. It's the area under the curve to the left of that. On this CDF, I might say that it is not an area, it's an actual value. So your test score here, in the CDF, it would be a a value of 68 or 0.68. Okay, D. How far above the average graduate test score would an individual need to score in order to be classified in the high performance category? Well, the high performance category is the top 20%, this graph shows. And in other words, we want to know, for 20% here, what does the test score here, your test score, need to be? Now, we don't know in this question what the test score was being marked out of, so the best we could do is to give it in terms of a standard score, a Z score, and that will mean that we're effectively saying how many standard deviations above the mean you would have to be in the top 20%. So to answer this question, we want to know, again, I'll assume that the test scores are a random variable x, so we want to know the probability of x being that x is less than a particular score x, that is equal to 0.8, and that 0.8 is that if there's 20% of people above, that means that there must be 80% below. So we're wanting to find this value x for which there's an 80% chance of getting lower than that. And in fact, I probably could do better here. I'll say that in fact it's the probability of a Z score being less than a particular value x. That's equal. We want that to be equal to 0.8. The easiest way to do this is to use Excel. Excel, what we'll do is use the norm standard distribution, so norm S. What are we wanting to find here? An x value, so that means we need to use the inversion. And Excel is going to want to know the probability of getting less than the x value that you're interested in. So we'll say 0.8. In Excel we'll put equals, and that will give us the answer. Now, let me just quickly check what my answer for that was. Uh, 0.84, roughly. So, it seems that if you want to be in the top 20%, you need to be at least 0.84 of a standard deviation above the mean value. And finally then, to question E, why are the descriptions of the performance categories framed in terms of likelihood? Couldn't they be more definitive in interpreting an individual's result? The reason for them expressing uncertainty, which is this likelihood thing, is because they're trying to measure your aptitude, or perhaps your strengths, but they're doing so by like a sample of questions, and it's on a particular day, at a particular time, and you're being compared to other people who are also subject to this same kind of sampling process. And so that's why they can't be 100% certain of their interpretations. It's because effectively sampling is being used. And that is the end of question 4.